So in this part, now we're going just to have a quick look at the engineering equation solver and see what we normally do in problems associated with this program. Actually, it's a very powerful program which is providing sort of solution to many problems that we are facing, and it has very good features. Part of the features that it has is that it basically provides us with properties that are built in, and this is a very good thing to have. And it is basically providing us with solutions that are simultaneous. For if you need to solve simultaneous equations together, then EES is the best venue where you can find this. So I'm just trying to see that I should be able to share it. I'm just having so many open files in the system. I'm trying to close them all. So that I would just see where is that file so that I can call it for. Okay, so Adobe, no. It's just taken me a while, so excuse me for this. I'm just trying to see where can I open that. I think I did that before. The only thing is that I'm not seeing it. Basic looking for. Are you able to see it now?
Yes.
Fine. So actually, what you see in front of you is the example that we had today. But let me start a new file, which is here. This is the platform of the engineering equation solver. And if I need to solve equations together, then the only thing that matters is that the number of unknowns is equal to the number of equations. This is all that you have to worry about. How to write the equation, it doesn't matter, which means that in some languages before you had to write the equation like that. For example, we can say that if temperature of the feed is, it doesn't make a difference whether it is capital or small letters, that's fine. So suppose that a problem like this, the feed temperature is 45 and T1, for example, is equal to 56. Let's assume that. And then the CP is 3.88, for example. Then the mass flow rate of the feed, for example, is, say, it is 2.5. So now each one of them just writing the equation. If I need to calculate, for example, what is the heat transfer rate, then it should be, for example, M feed into CP into the temperature difference T1 minus TF. So we have 5 equations, we have 5 unknowns, and accordingly, when I press on this calculator, it should be able to provide me with every one of these. Now, one more thing which is related to Q or to working with the ES, which is related to properties. Suppose, for example, that I need to say that this Q is equal to M steam into HFG of steam. And I know that steam temperature, for example, is equal to 70. Let's say that. Then the value of HFG, normally to get it, you go for like thermodynamic tables or maybe property calculators at the internet and get the value of HFG. For us, all you have to do is this: options, function information, and thermodynamic properties. This is what we are interested in. And in the thermodynamic properties, you have a long list of materials here. The one that we are going to use is steam. Here is it. I'm looking for the enthalpy of evaporation. It has so many properties that can be calculated, which are basically compressibility factor, Cp, Cv, density, enthalpy, entropy, whatever. So it's enthalpy of evaporation, which is given as a function of temperature. So this is basically is given to us here as a function of Ts. And I'm going to call it HFG, so I'm not going to use this, it's HFGS. When I paste this, then I have the equation here. Now, if you change the value of Ts, then this one is going to be changed automatically so that you don't have to recalculate every time. It's been already calculated here based on this value. When I run this, then I can get the value of m dot steam as you can see it here. So this is the sort of analysis that you can see from a unit like this. I mean, from using EES. It's not only the HFG which is used, but whatever that you need. If you go back to the HDH units, and for example, you need to calculate, I'm writing things, I'm not writing a program, I'm just showing cases. For example, that you need to calculate enthalpy for the air, which is leaving the humidifier at a temperature of, say, 39 degrees centigrade and relative humidity of 90%. Then temperature T-air2 is going to be 39. And relative humidity, let me call it phi, is equal, this is the relative humidity of air, and phi is 90%, which is 0.9. Then I need H of the air at 2. Then I'm looking for enthalpy of air, and I'm given the dry bulb temperature and the relative humidity. So I can go to the options, function information, thermodynamic properties, and I'm dealing with air-water systems here. And for air-water system, I need the enthalpy based on temperature, dry bulb temperature, and relative humidity ratio, which is phi here. So I've already written H-air2. I don't have to copy it. So it will be enthalpy of the air at, no, it's not humidity ratio, it's relative humidity. So,
Doctor, pardon me.
yes.
Why the temperature and the relative humidity are independent properties?
It can be temperature and omega. It can be relative humidity and omega. Any two of them. You have a list of properties. You can select any one of these. Temperature, wet bulb temperature, dew point temperature, humidity ratio, or relative humidity. Any one of these can be selected with any one here.
Based on the given information.
Based on the information given in the problem, yes. The information that you know. For example, in this case, I know the value of TA2, and I know that the relative humidity here is phi. And it's asking for another thing, which is P. Now, if I'm going to put this here and I'll solve, it will give me an error. Why the error? Oh, sorry, here because it has one more than one equal sign. It should be only one equal sign. But why is the error I expect? Because I have 11 equations and 12 variables. What is the variable that I did not specify?
I maybe.
R.
No, R is, I said R is equal to phi, and phi here is 0.9. But it is that P1 that I did not mention. So I should here state that. How do I know that? Sometimes you have a program which is something like 20, 30, 40, 100 lines. And you solve and you tell you the number of equations is not equal to the number of unknowns. To check first number of equations, the number of unknowns, I press on this, that equal sign. then it would tell me I have 11 equations, 12 unknowns, but it did not give me the details. Maybe when I press, it asked me, show debug information. Do I need to debug it? Yes. And when I debug it, I look at this. I normally look at the parameters which are listed only once. And here, HE2 is listed only once, but I know that I'm calculating in terms of other parameters. So yes, it should be there. MDOS team listed only once, but yes, because we are calculating it. But P1, it is listed only once, which is here. And I'm not calculating P1, it should be an input value. So that's the one which is missing. So that gives us a hint, the information that are listed only once. One of them would most probably be the parameter I'm looking for. So P1 here, I should, and there's no specific order. Then I can put it before the equation, after the equation, does not make a difference. This is 100 kilopascal. And then when I'm trying to solve, then I'm getting here HR2 as 146.8 kilojoule per kilogram. So this is essentially the idea of operating that software, which is the EES. But it has much more features compared to what I'm showing you. Basically, what we have been using is writing the equations. Number of equations is equal to the number of unknowns. The order is not important. For example, I can come to this equation and say that MS into HFGS is equal to Q. So whether you write this on the left or right and right does not make a difference. And this is a very good feature of flexibility in this program. In some other programs, you have to write the unknown alone at the left-hand side and the rest at the right-hand side. We don't do that. You write in any order, whether it is capital case or small case does not make a difference with the program. And that's another good thing that we have here. And one more important issue is related, for example, to the parametric analysis. I may give you a problem and say, for example, how much will be the effect of it changing? Let's say, for example, what if we change the value of TF here, the feed temperature, and say the feed temperature is going to change. Let's talk about a case which is that we have been considering a while ago. And we say that we have a case of MD is equal to 1 kilogram per second. And we have, we need to know the vapor temperature at state number 1. So HFG1. So I need now enthalpy of evaporation, but at another condition. I can follow the options, properties, thermodynamics, or simply I can copy this, Control C, Control V, and change this to be T1. And say that I'm going to say in the energy balance, it is M dot F Cp delta T plus MD into HFG1. If I run the program, it runs like that. You can see it here. And then what I need to test, how much will be the effect of changing TF, the feed temperature, on this equation. Remember, this equation has two parts. Part of it is, I'm going to highlight it in yellow. Part of it represents sensible heating and part represents latent heating. So now let me see, what if I change the feed temperature? How does it affect the value of Q? So to do that, I need to remind myself, this is what I'm going to do. To start a comment, something that you write for yourself. I need to change TF to see its effect on Q, for example. And here, when I come to this part, I can, for example, be writing that. You see, I use the double quotations here to write a comment. Now I can write also this curly bracket for a comment. I'm going to check the psychrometric properties through that program. What I'm writing here, because if you are writing a program and you worked for some of it today and then you left it for a couple of days and you need to come back again and open the program, you might forget what did I do that and what I was doing here or there. So writing comments here, it's called documentation of the program. And this is extremely important, especially if you are writing large programs. You see in the solution, this has been turned into blue, because blue, it means that the software does not look at these. These are comments for yourself. So if I've written a program a couple of years ago and I need to open it again, then I need to know the details. Writing as much as possible of these comments is going to help me remember what I was doing here and what I was doing there. Like I'm teaching this course almost once a year. So sometimes I need to modify a problem and then I get into the EES and try to look at the details and then put the modifications I want. So I don't want to spend much time on remembering what was I doing here? Why did I calculate this or that? But I can write as much information as I want. One more thing here is that I can put units. For example, temperatures are in centigrade. And these square brackets are looking at this kind of information here. This is kilojoule per kilogram Kelvin, for example. And then when you are putting the solution, you see it will come here along with it. What I've written there is coming here as units. This is an additional thing that will not affect the solution, but that's something you do for yourself so that you would, when you come back to this program, you would know, yes, it's easier to remember every one of these parameters that you are putting here this way. You don't have to, you can even organize it in a way that I'm going to put it like this. These are some of the features that are not very essential in the program, but they are very good additions, as you can see here. And each thing I write here, it will come here as, or the units will be given. The warning here is that 4 potential unit problems were detected. This is basically because I did not put the units for every one of them. If you do it, probably this thing is going to disappear. Now, here comes one of the excellent features in this program. I said I need to see the effect of changing the feed temperature on Q. If I'm going to solve that by hand, I'm going to select another value of TF, calculate Q, another value of TF, calculate Q, and then put it in Excel and draw it, for example. What I'm going to do here is the following, because this is the parameter I'm going to change. So I'm going to comment on this line as if this line is not there. Can I run the program this way? No, I cannot. Why? Because the number of equations and number of unknowns is not equal. Oh, this now because I commented on this, so it will, the square bracket does not have a meaning. So let me comment it all. If I try to run this, it will tell me that the number of equations and number of unknowns are not equal, and this is true because I hid this value. This is hidden, so I cannot solve the problem. But what I'm going to do here is I'm going to go to this and say that I'm starting a new parametric table. In this parametric table, I'm changing the value of TF, which is this, and I want to see the effect of changing TF on Q. Do I need to see anything else? No, this is basically what, because the rest are constants. I can put more and more. For example, I can put MF, I can put MD, but I don't need these values because they are not going to change. But what will change when I change the value of TF? The value of Q is going to change. So this is what I'm going to change. When I click on this, it will open another table for me. I need to change TF. So I need to change it from what value to what value. So I click on this. I need to change it from 20 to, for example, 50. Here is, it has divided this between those. Suppose that I don't need, those fractions are coming automatically. You don't have to worry about them. For example, if I want to solve the problem, all I have to do is press this green arrow, and it will give me the value of Q's right away. So when I'm talking about a parametric study, I don't really have to calculate Q 10 times as you can see it. I just put it here and it will do it for me. Now this will tell you, and that was a part of the question that has been raised probably by Khaled when we have solved the previous example. When should we account for the sensible heating and where we should not? Now the answer is here. How significant is the change of Q with respect to the changing of the sensible heat part? I'm changing the sensible heat part in terms of the value of Q. Maybe if the TF is going to change from 45 or 46 to 50, that change is not significant. This is negligible. But going from 20 to 50, now that can be a substantial change. We're talking about something like 300 300 in 2000. We're talking about something like 10% change. Is that all? No, because one more thing is that this result that we got here, we can plot it. So for example, if I'm going to ask for a new plot window, the x-axis will be the TF, the y-axis will be Q, and here is it. So how the TF value affects the value of Q, and look at the values of Q here, they are changing from 2,400 to 2,750 or a little bit less. I can play with the with these parameters in a way that I can look at the properties of this figure. For example, I want the values here for the y-axis. I can do smoothing if you have scattered values, and you can change the line color, you can change this kind of properties the way that you like so that the figure looks better. And what I was thinking here is that there should be a way, I just forgot that, there should be a way that I can control I can control the scale. I'm sure it's there. I'll just leave it for you to look at. That's something that you can find out. But this is basically some sort of a way that you can do a parametric study, and you can plot the results that you have. It's between Q and T and TF, and then here is that it's shown to us. So this is a very powerful sort of program. So all you have to do is number of equations equal to number of unknowns. You have a very rich property database that will give you many of these. Suppose, for example, something, I just remembered it. So now I'm talking about the value of CP is equal to 3.88. This is a property. Shouldn't it be there? The answer is yes. The point is, what is the CP that we're looking for? I can, for example, say that I need thermodynamic properties of real fluids, and it is basically water. Here is it. And I need enthalpy, which is not enthalpy, I need the CP, specific heat, CP of water, as a function of temperature and pressure. The temperature here is, say, it's going to be TF, and the pressure again is going to be P1, which is the 100. So when I'm looking for the value of CP here, it should be calculated automatically. I need, in order to be solving the problem again without the parametric effect, I need to remove this and then run the program. Now what is it? Legal variable name. There's something wrong with the variable name that I used, is it?
Yes, doctor. The capital TF you should use, I believe.
No, capital and small does not make a difference.
Ah,
But you make it capital in the equation.
Let me try. It tells that illegal variable names must begin with a letter. It's not seeing that what I'm doing is basically a letter. So again, it is CP. Oh.
I think the unit which you write.
It should not be, yes, yes, you are right. This is because the units can be written whenever you have a numeric value, but whenever you have an equation, you cannot write the unit for it. So here the value of CP is calculated to be 4.18. This is for pure water. What if I'm not using pure water? What if I'm using salty water? Then do we have properties of seawater built in here? The answer is yes, and you can find these in the external routines. And I think we have communicated with the author of this software so that he would add the seawater properties in. You can see for people interested in heat transfer, there is a lot of information for the heat transfer out there. For example, fin efficiency, fouling factor, free convection, heat exchangers analysis. So a lot is there. And here there is, look at the mouse, there's examples here, and there's a lot of made programs. For example, you can get a whole example written on Rankine cycle. You can take it and change values, and then you have a running Rankine cycle program. Now, what I'm looking for is basically seawater. Yes, seawater, here is it. So in the EES library routines, this is something that has been added by our group actually. We have worked with the seawater properties, and once we made them complete, we communicated Klein, who's the author of this software, and we told him that we have created this reliable seawater properties, and he liked that, and he said, I'm going to include it in the library. So he did that, and we have the seawater properties are there. What did I do here? I was looking for functions here for the seawater properties. Let's open the seawater properties. And for example, seawater, if I'm looking for the specific heat, yes, seawater specific heat. Here is it. It's a function of temperature, salinity, and pressure. So I'm going to take this value, and I'm going to paste it here, that it is basically the seawater properties that, but I have to put here that the pressure is P1, temperature is TF, and the salinity, I have to write the salinity, which is written here, if it's 45,000, I should divide it by 1,000 because it's given as gram per liter or per kilogram. When I run it, I've removed this somehow. Yes. This should be.
The middle quotation, maybe you have to remove it.
Oh, yes, it's because of the quotation. Actually, this thing should not be there. Now, it's out of range. And this is one of the things that you may face sometimes whenever you are putting this, that sometimes you are putting equations that are bringing you out of the range. And you have to be careful whenever you are using, because if you remember, for example, in the heat transfer correlation, we used to have something like an equations for Nusselt number, and this equation is applicable for Reynolds number between this range and that range, and for Prandtl number between range and that range. If it's out of the range, it may either give you an error or it will not work, like what's happening here. So which means that some of the parameters that I put in this expression here are out of range. Let me see if this is the one, because the pressure that we are using is basically 100. And there's another issue here, which is related to the units. So the units here, no, it's basically I'm trying to see what was the unit system that we use for this. For this unit, you can change between international to bridge system of units, or consider, for example, your values are expressed in kilopascals or megapascal. Temperatures are given in centigrade or Kelvin. Unit system is SI or English, and then units of joule are given as energy joule or kilojoule, mass or molar basis. So this all you need to make sure that they are correct as well.
From where again, Doctor?
Excuse me?
From where did you get
Options and unit system.
Okay.
So in the options, we have used a couple of things. One of them is the function information. This is where you are getting the properties. And in the options also are getting the unit system. So what we've done here so far is some sort of a brief introduction to the software, how you can write equations in, how you can solve it, how you can make a parametric table and plot your results. The program has much more than that. So it has a very good help. I would suggest that you go for the help index and go through it. Actually, you are going to do that as much as you need. So whenever you have a problem, you're going to go to the help. And sometimes it would be useful to look at this long list of examples that it has there. For example, if I'm talking about examples in thermodynamics, then when you look at this, it will give you a list of thermodynamic problems that you have here. So these are examples. Some of them are for about throttling process, a heat pump cycle. What else? You can have a Rankine cycle here. You can have so many. And the same thing applies. You have even ammonia water absorption system in the software. So it has a lot of examples that you can make use. And whenever you have a problem, you can get back to it, see an example which is closer, and then you can learn a little bit more about it. So I hope this would be helpful in helping you, especially those who did not use the software before, to be able to write their projects in. And as I mentioned, it will be available on almost every day except for Thursday at 1 o'clock, and then to receive your questions if you have any.
Doctor, I have small questions.
تفضل يا عبد الله.
Doctor, I believe we don't have the seawater properties in the EES in the demo.
Yes, because the demonstration will not provide this. It's only for the licensed version. So what I'm going to propose is that you just use the properties of water in your work.
Okay, Doctor. I have another questions about should we use the enthalpy or we can use the CP delta T?
If you are using, if you are going to use the EES, I prefer that you use the enthalpy. It's built in and it will be calculated for you. The CP delta T is some sort of a rough way to calculate the enthalpy if you have no other means. But if you are going to use EES, you better consider the enthalpy.
Okay, thank you, Doctor.
You're most welcome. Any other questions? That would be it for today, ya shabab. Just we are like 5 minutes late. So sorry for that. And if you have questions, I'm still here for about 5 more minutes.
Yes, Doctor. Regarding the system, for example, if I to get the properties of the vapor, system I choose the air H2O system or
if you are
real fluid, for example.
HDH systems, you're always going to use air H2O system. It is not air because it's dry air, and this is misleading. So it's got to be air H2O.
Whether the properties are for the vapor or for the air itself. I mean, for the water or the air.
No, for the air, you are talking about water. I mean, for water, it's water. But for air, it should be humid air, which is the air H2O. It does not mean water. It means air with humidity, humid air.
Humid air. And for the
Humid
water,
air.
for example, if I
For the
want
water, you just go for the water properties right away. Which is, if you recall, we've just used that. Here is it.
Yeah, the thermodynamic
For
properties.
options, functions, and I need water. Then water will be real fluids. And for the real fluids, I'm going to select water. So water in the HDH systems is going to be this water. Since you don't have seawater, then this is the one that you are going to use.
Clear. Thank you so much.
Okay. And if you use air in the HDH system, then it will be this air H2O, which is humid air.
All right. Thank you so much. That
You're
was
welcome.
so beneficial, Doctor. Appreciate it.
You're welcome. Any other questions يا شباب؟
معلش.
داوود اتفضل.
If I put the wrong unit, it will recognize that or not?
No, no. When you are dealing with a computer, whatever you give as value, it's going to process. It will not ask you what are the units that you put me here. So you have to be careful.
Okay, thank you.
If you remember the first course, we have probably all of us learned about computer. It's telling us that computers are machine and they are adopting what's called GIGO, garbage in, garbage out. If you put anything in, it will give you something at the outlet, but you have to be able to make sure it's correct.
Okay, thank you.
Doctor, I have a question.
اتفضل يا أحمد.
Can I share my screen just to make it even clearer?
Yes, give me a second. Yes, Ahmed, you can share it. Let me stop sharing. You can share